for 15.6. If you didn't notice the theme, first we learned about line integrals and how to compute them, and then we said, here's all the applications that we have. Mostly work. Okay. Yesterday we talked about surface integrals, and now we're going to look at some applications of surface integrals. Mainly, something called flux. Does it sound familiar because of Back to the Future? Is that why?
I don't know why it's in the
Okay, so first let's talk about flow fields, okay? So we're going to think about the vector field f of x, y, z, representing velocity of a fluid particle at the point x, y, z. Okay, so for our force vectors, just to help with the interpretation, think of the vector field, all the vectors are just velocity vectors. Okay, so it tells us the velocity of a particle that's moving along the vector field. Okay? We'll talk about an oriented surface. What we mean by orientable is that the surface has two sides. Outside and inside. We will only be dealing with orientable surfaces in this class. However, it's worth mentioning one of the most famous examples of a non-orientable surface. This would be something that maybe just has one side only. And Carl, you're right. Have you guys heard of or seen a Mobius strip?
Oh, I have.
All right, then let's move on.
No, hold on. I want to see you draw it.
Oh, I'm not going to draw it, but
Oh.
I will use this piece of paper to illustrate. Okay, so if you take this, I should probably trim it a little bit. Okay, if I connect this piece of paper like that, you guys see that there's a top and a bottom, or an outside and an inside, right? If there were a little bug walking along this surface, it would have no way of going to the other side unless it, like crossed over. Okay? Now, if we take this point and we actually twist it and connect it like this, now this is this is the Mobius strip. We say that there's really only one side because if you're walking along the surface here, one could theoretically traverse the whole thing without having to cross over. Does that make sense? Okay, so this is an example of something that's not orientable. We're not going to deal with any of these, but this is a Mobius strip, okay, in case anybody was curious.
Is there a picture in the book?
I think there is. If you want...
Show it or no? It's kind of cool. I don't know.
I like mine.
All right,
Carl's making his own Mobius strip. Okay. All right, so as I said, we're only going to deal with orientable surfaces, all right? Now, let's look at one.
I'll just find one. There's probably one in this game. Or rats.
Here's a surface. We're going to say that n is a unit vector at each point. So at each point, there's going to be a unit vector. We'll call that n. Negative n will just point the other direction.
Bless you.
So we'll say these are all representative of unit normal at a point. And if I drew in these would be negative n. Okay, the other thing worth mentioning is that these unit normals will never have an abrupt change in direction. Meaning, it's impossible, so if I have a surface here, for us to say, here's n, here's n, here's n, and then, oh look, all of a sudden n flips over and is now upside down. Okay? So if these are all n, this will never happen, where you have the unit normal, the positive unit normal, all of a sudden just switch directions and flip over. Okay? Now, these could very well be negative n, but not positive. Okay? Now, the orientation of a surface, actually we'll clarify, an orientation of a smooth parametric surface is defined by the unit normal. And we calculate the unit normal by taking partial r, partial u, crossing it with partial r, partial v, and to get a normal vector that's a unit vector, we have to divide by the magnitude of that vector. Should look somewhat familiar. Okay, we call this the natural orientation. And again, this is for a surface that's parameterized as r of uv equal to x of uv, y of uv, z of uv. Okay, in fact, this will be called the positive orientation as well. So if we're interested in positive, if we want to know which way is positive, we'll say positive will just be defined by n. Whichever way that points, that's our positive orientation. So for instance, do a quick example. if we have the surface R of uv, defined by cosine u v, and then negative sine u, and we'll say that u is between 0 and 2 pi, bless you, v is between 0 and 3. What shape is this, by the way? It's you're thinking correctly. If we ignore this v, okay, it's a circle, right, along the y-axis. And now we're just going to, since they tell us that v is from 0 to 3, we just extrude that circle along the y-axis until, since y equals v, right, from 0 to 3. Okay, so now if we actually found, what time do we get out of here? We get out of here like now, don't we? Or
Yeah. No, I have 13.
oh, that clock is fast,
Yeah.
and it's 54 a.m.
Yeah.
Not p. Okay, I was like, man, I'm really behind where I normally get to. This is awful. Okay, so let's find the orientation. So if we take partial r partial u crossed partial r partial v, this will paint a picture and tell us which way the normal vectors are pointing at each point. So we can kind of sketch one or two and get an idea for which way is positive and which way is negative. So partial r partial u will be minus sine u, 0, and then negative cosine u. Partial v will be 0, 1, 0. So then we actually get the vector cosine u, 0, negative sine u. So what's the magnitude? Yep. Okay, so the unit normal vector actually looks suspiciously like our original parameterization. So let's see what happens. Okay, so now what this means, let's check a point. So at, let's say, u equals 0, v equals 0. What does that correspond to? So that means here, right? Now, when I plug in, so you guys see 1, 0, 0 came from our original function that tells us where we are in the surface, right? And now if I take u and 0, u equals 0 and v equals 0 and plug it into n, what's our normal vector going to be? It's the same exact thing. So what this means is that at the point 1, 0, 0, there's a normal vector pointing one unit in the x direction and then 0 for all the other components. So here's our normal vector. And just from this one picture, you guys see what's going to happen, right? Basically, outward in this case is positive. As you go around the cylinder, the normal vector will just be pointing away from the cylinder. That's the positive normal vector. Okay, negative n would be pointing inward towards the y-axis. Okay? So in this case, outward is positive, inward would be negative. Okay.
How do you know it's along the y-axis?
Because actually these normal vectors have no y component ever, right? And if we change the y value for v, we're just going to move along the y-axis, but it's going to be the same vector. Okay. So the last thing we'll talk about. Go ahead and define flux. Okay, but first, some conditions. We will only deal with incompressible fluids, uniform density, that's what that means. So we're not going to have any strange things going on here. Everything's going to be exactly what you would expect it to be. We'll also assume that the velocity of a fluid at a fixed point does not vary with time. This is what we call steady state. So, for instance, the surface that we had above, if I was at one particular point, we would say that at that point the velocity is going to be the same. It's not going to change over time. We're not going to have anything crazy like that. Okay? Now the idea here, so here's the definition for flux, and we'll talk about what it depends on. Flux is defined as the volume of a fluid that passes through a surface in 1 unit of time. Here's what it depends on. 3 things. 1, if the velocity field is slow versus fast, which one would have more stuff flow through the surface? The fast one. So, speed of the fluid is one thing it will depend on. Greater speed means greater volume in the end. 2, how the surface is positioned relative to flow. So in other words, if I have a surface that looks something like this, and here's my flow field where everything's parallel. So I know it's hard to see on paper, but if you imagine this representing a surface and then velocity vectors that are just running parallel to this, right? What's going to flow through the surface if we're going this way? Alicia? Nothing. If the flow field is perfectly parallel to the surface, nothing's going to get through there. Does that make sense? But now if I turn the surface so that it's perpendicular, that's actually the best position for it, right? And I have everything just shooting right at the surface. Does that make sense? That stuff's going to get through a lot better there. So depending on how it's positioned, so this is no flow, or no flux. But if I have...
This is really like a permeable...
Yes, we're assuming the surface is permeable, yeah. So we're not going to have a bowl where we have water flowing through and then it just collects. No, it's going to get through. This is a great position here. So if we have the flow field perpendicular, this is max flux right here. And the third thing, obviously, is the area of the surface. If the surface that we're interested in is small, well, then not much fluid is going to flow through that permeable surface. But if we have a large surface and we have a vector field or a velocity field, then we're going to have a lot of stuff that goes through it. So bigger the area equals more flux. Okay. This is a good place to stop.